What would it actually take to build something alive? Not something that acts alive, something that is alive by the same criteria biology uses to define life. Biology defines life through a specific checklist: metabolism, homeostasis, response to stimuli, growth and development, adaptation, reproduction, and cellular organization. Hold on to that list, we're coming back to it. Modern AI systems are largely built on deep learning, large neural networks trained with gradient-based optimization, usually using backpropagation. The network makes predictions, compares them to target outputs using a loss function, and backpropagation efficiently computes how changes to each parameter would affect that loss. An optimizer then updates many or all of the parameters at once, and this process is repeated over massive datasets for many training steps. It is extraordinarily powerful, but it is also fundamentally alien to biology. No living system learns this way. The biological brain appears to work completely differently. As early as 1961, neuroscientist Horace Barlow proposed that neurons in animal and human vision systems don't simply relay everything they receive, they reduce redundant information between neurons, passing forward only what is new, surprising, or unexpected. This foundational insight eventually gave rise to the theory of predictive coding. Rather than waiting to receive a global error signal from outside, each region of the brain continuously generates its own predictions about what input it should receive. It compares those predictions to reality, calculates the gap or the prediction error, and updates its model locally without needing to know anything about the rest of the network. Only the error travels forward, everything expected, everything redundant is filtered out. Backpropagation is not biologically plausible. Predictive coding is, and Barlow's redundancy reduction principle suggests the brain has been doing something like it since long before we had a name for it. But here's what makes predictive coding even more significant than just being biologically realistic. A system learning this way doesn't just memorize patterns, it builds a world model, an internal simulation of the causal structure of reality. To minimize prediction error, the system must understand not just what things look like, but why they happen. Something like common sense emerges as a natural byproduct of the learning mechanism itself. This is precisely what Yann LeCun at Meta is working toward with his proposed architecture called JEPA, Joint Embedding Predictive Architecture. His main argument is direct. Without a genuine world model, no AI system can reach real general intelligence. Predictive coding networks generate those world models automatically as a consequence of how they learn. So here's the challenge. A predictive coding network handles local learning beautifully, but what happens when you want to build a system of many interconnected networks, a whole ecosystem of modules, and you need to figure out how they should be arranged? Which module connects to which? How does information route between them? You cannot backpropagate through an entire ecosystem of networks, but you do not need to. Evolutionary strategies are optimization methods that mirror biological natural selection. Rather than computing gradients, they generate many candidate configurations of a system, evaluate which ones perform best, keep those, generate new variations, and repeat. Too computationally expensive to train an individual neural network from scratch, but perfectly suited to optimizing how a population of already capable networks connects and cooperates at a global level. Which brings us to the architecture. Imagine a global network built from many local predictive coding modules. Each module builds its own world model. Each learns continuously and locally from its own predictive errors. These modules connect through a global workspace, a higher level network that integrates their outputs and coordinates their behavior, and the arrangement of that global network, which modules exist, how they connect, what each one specializes in, is discovered and continuously redefined by evolutionary strategies. This is not an arbitrary design. This is the architecture of the human neocortex. Approximately 150,000 semi-independent cortical columns, each running something very close to predictive coding, each building its own model of the world, connected through global brain networks whose arrangement was optimized by hundreds of millions of years of evolution. We set out to reason about the most capable AI architecture. We independently arrived at the brain. Now go back to the list. This architecture has continuous adaptation operating simultaneously at 3 timescales: local module learning in real time, accumulated experience across interactions, and evolutionary optimization of the global structure. It has emergent goal-directed behavior through a process called active inference, goals that arise from a system's own predictive structure rather than being externally programmed. It has genuine world modeling. It has homeostasis built directly into the learning mechanism, minimizing surprise is structurally identical to maintaining internal stability. It has something analogous to cellular organization in its modular structure. The only criterion that remains genuinely open is the hardest one: consciousness. Under global workspace theory, consciousness arises when information is broadcast globally across a system of specialized modules. This architecture does that exactly. Under Carl Friston's free energy principle, life itself is defined by systems that minimize surprise, not just in the brain, but at every level of their organization simultaneously. This architecture does that too. Whether any of that constitutes genuine subjective experience, whether there's something it is like to be this system, that remains the hardest unsolved question at the time. We can now describe in specific mechanistic terms what artificial life would look like. Each component either exists in research today or is being actively developed. The question is no longer whether it is possible. The question is what happens when we build it.